Hi everyone, welcome to the beginning of Unit 3 of our regular physics class. In this unit we're going to be discussing circular motion, that is, in particular, mainly uniform circular motion, where an object is going around a circle at a constant speed. Now, in this particular video we're going to introduce some fundamental concepts and then get to the acceleration involved in uniform circular motion. So when we say uniform circular motion, as we mentioned, this is circular motion where the speed does not change, but is also not zero. But this means that the velocity is changing all the time. So how can that be true? Well, the answer is because even though the speed doesn't change, the direction does change, which means that the velocity vector, which is you can imagine pointing from where the object is in the circle in the direction of the motion, the velocity vector itself is always changing. So we need to introduce some vocabulary, and then soon we're going to show how the velocity vector changing means that there is a particular type of acceleration involved. So first, when objects are traveling in a circle, they undergo a complete revolution, that is a complete orbit around from point A back to point A in one period, capital T. So we use the symbol capital T to denote the particular time that it takes to go around once, whereas lowercase t is just kind of like any time coordinate. So it's the time to complete one cycle. So the time per cycle is just going to be any time units. So the period is going to have any time units, but in SI units, that's going to be seconds. Now the inverse of period, which is the number of times it takes to go around, or the number of times it goes around per second, is given by the symbol lowercase f. That's the frequency, and that's the inverse of the period, the number of cycles per second. So if you tell me that the period is 2 seconds, then I will tell you that the frequency is 1/2 seconds, that is 1/2 of an inverse second. And after a while, people got tired of writing inverse seconds or cycles per second all over the place when they were talking about frequencies. So they just abbreviated that unit with a unit of its own and said that an inverse second is called a hertz, capital H, lowercase z. And another commonly used frequency unit, particularly dealing with car engines and stuff like that, is revolutions per minute, or cycles per minute, or strokes per minute. So lowercase f is typically used to denote frequency of just ordinary cyclical oscillatory motion. But I should mention that you'll also sometimes come across frequency in having to do with things like sound as well as with light. With sound, frequency is also often given by the symbol lowercase f for cycles per second. But when we're talking about light, a lot of times the lowercase Greek letter nu is used for the frequency for that. That will not concern us in this course though, but I wanted to mention it to you because you might have come across this before. So some other definitions, well, one revolution, that is one cycle, is 360 degrees around a circle. So frequency is number of cycles per unit time, whereas period, again, is the inverse of that. That's time per number of cycles. And RPM is often used as the symbol for revolutions per minute. It'll either be capitalized or lowercase, it just depends. But in any case, since period and frequency are inversely related, you must remember that period equals 1/f. In fact, that's really the definition. So, quick practice, a turntable rotates at 33 RPMs. What's its frequency in SI units? Well, we can do a quick unit conversion. Say, in fact, this one in the middle is maybe not completely necessary, but a cycle is 1 revolution. And then convert minutes to seconds, 1 minute per 60 seconds. Another quicker way of doing this would have just been to first express this as 33 revs over minutes, and then substitute in 60 seconds per minute in the next step, and you'd still have 33 divided by 60, which would be 0.55, so 0.55 hertz. About little Bobby Bolo swinging a bolo around 3 times every 1.4 seconds. So what's the period and frequency of the rotating bolo? Well, The period is time divided by number of cycles, so 1.4 seconds divided by 3. So that would be about 0.467 seconds for the period. And the frequency is the inverse of that. So 1 over 0.467 seconds, or 1 over 0.4666666, etc., since we don't round until the end when we do calculations. And that ends up rounding to 2.14 hertz. Now, given the fact that these objects are moving, they have a velocity, and we have a name for this velocity called tangential velocity. The reason we call it that is because if you were to draw the velocity vector for the object, like let's say it's right here in its circular motion, then the velocity vector would look like this. In other words, at this particular time, it's moving in this direction. So, well, that direction is tangent to the path of the circle. So that's why we call it tangential velocity, but it always points in the direction of motion. So what is it? It's the speed that the object is moving around the circle. But to figure that out, you think, okay, speed is distance divided by time, but the distance around a circle is the circumference of the circle. That is 2 pi r, where r is the radius of the circle. And by the way, when we're talking about circles, for the radius, we can either use lowercase r or capital R, just depending on the situation. And sometimes they can be thought of as interchangeable, but in fact in this course they pretty much always can. So it's okay to call it capital R in this case. But little r is usually just some typical radial coordinate. And the time around the circle is the period. That's capital T. Well, distance divided by time, so tangential velocity must be 2 pi r over t, circumference divided by period. That's how we can remember it. It's circumference divided by period. And you should know the circumference of a circle is 2 pi r. Back from previous math. Now, a lot of times we use the subscript lowercase t to denote that it's a special type of velocity, the tangential velocity, the speed of a particle around a curve. Now, time versus period, we already kind of introduced this a little bit, but we're going to end up coming across this in an example in a little while. But the period for just any sort of cyclical motion can be thought of as the total time divided by the number of cycles during which you were watching. So, let's look at an example. Mr. B, hey, that's me, swings a weasel in a circle of radius 1.3 meters. If the weasel completes 42 complete loops in 10.0 seconds, calculate the tangential velocity of the weasel's nose. In fact, I believe I took this exact example from a class one time. So, 42 loops in 10 seconds in a radius of 1.3 meters. So let's see how that works. So the period is the time divided by number of loops. So 10.0 seconds for 42 loops. So there's our period. Tangential velocity, 2 pi r over period. So we plug the numbers in. So we have 2 pi times the radius divided by the period. That turns out to be 34.3 meters per second. That's pretty fast. That actually translates to about 75 miles per hour. Okay. So, next example. A squirrel is chasing another squirrel around in a circular uniform speed. The squirrels are traveling 5.2 meters per second while playing like that. Calculate the radius of the circle if they're each timed to complete one loop in 2.26 seconds. So in this case, it's basically the same as the last problem, except this time we're trying to calculate the radius instead of the velocity. So here's your typical picture of squirrels playing. So you have your tangential velocity being given, and the period is also being given, and solve for the radius. So we start off with our formula, v equals 2 pi r over t, but since we're being asked to solve for the radius, we want to get that by itself, so multiply both sides by capital T, divide both sides by 2 pi. And, plugging in our numbers, we get a radius of 1.87 meters. Now, if I was to give this in a class, I would bet $10 that somebody in the class would end up getting, let me just check my calculator, hold on, times. I bet somebody in the class would end up getting about 18.5 meters for this, when the answer is actually 1.87 meters. They would have set it up completely correctly, plugged in the numbers correctly, but then they would have made a calculator mistake. A very common calculator mistake in problems like this is to not put parentheses in front of the 2 and then close parentheses after the pi. So the way that it should look in the calculator is you would do 5.2 star 2.26 divided by open parentheses 2 pi close parentheses. Because a lot of people just think that 2 pi goes together. And even when you know that 2 pi doesn't go together as one term, it's just so easy to make that mistake because we always see them together when they're actually written down. But no, 2 pi means 2 times pi. So if you didn't put those parentheses in there, the calculator would think that you wanted the pi in the numerator, and your answer would be off by a factor of pi squared, which is about 10. So that's something to keep in mind. Now, as we mentioned, the velocity is always changing with uniform circular motion. So if you're spinning a teddy bear that's tied to a string around in a big circle, well, that bear is accelerating because the velocity is changing. Even though the speed isn't changing, the direction of motion is, which means there's an acceleration. But as we know, whenever there is an acceleration, that means there must be a net force acting on the object. So that is something called the centripetal force. Centripetal means center seeking. In other words, it goes inward toward the center. The acceleration is inward toward the center. You know that because if you swing something attached to a rope around your head or something like that, you have to pull on it. But that pulling creates a tension, and the origin of that pulling force comes from the center of the circle where your hand is. If you get rid of it, then it's going to go in a straight line at constant velocity. So since it's accelerating, that means that maybe if we're crafty enough, we might be able to come up with a formula for this acceleration. So I'm actually going to prove this formula to you right now using geometry, and then kind of just imagining that angle getting smaller and smaller so that the geometry actually becomes correct. And then I'll give you a conceptual argument that you could use to maybe convince a third grader that it's true. I don't know about a third grader, but, well, we'll see. So, anyway, let's consider an object going around in a circle. And the object will be considered at 2 different points in the circle, at point A, and then after some later time at point B down here. Now, during that time, it underwent a change in angle of theta around the circle. The value of theta is not necessary. In fact, we're not even going to use the angle in the argument, other than noting that if you were to compare these 2 velocity vectors, the velocity vector at point B compared with the velocity vector at point A, that angle between them is the same angle theta. That's important because the change in velocity, which is the final minus the initial, which is this arrow right here, well, this completes a triangle. Not just any triangle, but a similar triangle to what we have right here. Triangle ABC is similar to triangle VA delta V VB. Those are similar triangles, which means we can take cute little ratios. So, just going back here, here's one ratio comparing delta V with VA. So here's delta V compared with VA. Well, with similar triangles, the whole thing about the ratios is that if you compare any 2 side lengths of one triangle, the ratio of those is equal to those corresponding side lengths of the other triangles. So this delta V over V sub A in this triangle on the right here must be the same as the length of this chord going from A to B divided by the radius of the circle. Oh, that's interesting. Well, that chord going from A to B, just looking back over here, that's almost the distance traveled between point A and point B. The real distance traveled is a little bit more than that, but the only reason that it's a little bit more is because I drew this picture big enough for you to be able to see. If you imagine drawing it, making the angle smaller and smaller, that chord length A to B is going to be the same thing as the actual distance that the object travels. Okay, so we'll just let that angle theta be small enough that that really is the distance the object travels. Again, just divided by the radius of the circle. So I haven't done anything fancy in the bottom or anything. I just recognized that that chord length, and in the limit where we let the angle become small, so that we're looking at this at one particular time instead of over an average, that ends up just being the distance. Well, wait a second, I know what distance is. Distance is velocity times time, or at least average velocity times time, and it's the same thing if we let the angle become small. Oh, well, that velocity, that's the same as the velocity down there. So here's what I'm going to do. I'm going to multiply both sides by this v sub a term to get this out of the denominator. And I'm going to divide both sides by delta t. Well, that's kind of cool. Delta v divided by delta t, I know what that is. That's acceleration. It's the acceleration we need. So that's where, when we multiply both sides by the v, we got the v squared term, and the r is left over. So there is our formula for centripetal acceleration. That's the formula for the acceleration of any object that is undergoing uniform circular motion. It's something that you must memorize in this course. It's a very important formula. And, of course, since force equals mass times acceleration, the amount of force you must provide in order to cause something to undergo circular motion is given by mv squared over r, and that is the formula for the centripetal force. Let's take a look at an example. So let's say the Tasmanian Devil from Looney Tunes spins around 800 times per minute. So let's find the frequency of the motion and then calculate the tangential velocity and the centripetal acceleration that a fly would feel in this situation. In fact, I'm going to skip the first two steps because we've already done something like this already. And I'm just going to show you how you can go straight to centripetal acceleration in just one mathematical, or at least one numerical step. So here are our givens. We have the frequency of the motion as 800 revolutions per minute. That is 800 cycles per minute, which I just immediately plugged in 60 seconds for a minute and converted this to 13.33 inverse seconds. That is 13.33 cycles per second, or 13.33 hertz for our frequency given. The radius of the motion is 25 centimeters. Well, we got to convert that to SI units as well, so 0.25 meters. And we're being asked to find the centripetal acceleration. Well, we have a formula for that. It's v squared over r, but we don't know what v is. In fact, that was one of the things the problem originally asked us to find. Well, we know v is 2 pi r over t, where t is the period. But they didn't give us period. But they did give us frequency. And we know that period is 1 over frequency, and frequency is 1 over period. So instead of calling this 2 pi r times 1 over period, I just decided to call it 2 pi r times frequency, because after all, the frequency is given. So there's my v. Well, how about I just plug this bad boy in for v right now? If a is v squared over r and v is 2 pi rf, then that means a is 2 pi rf squared over r. So square all that out. Don't forget to cancel a factor of r there on the r squareds there. So there's our formula for centripetal acceleration for this particular problem. So there's where we're at so far. Those are our givens. And now we plug in our numbers. And after plugging in our numbers, we get an acceleration of about 1,750 meters per square second. So very strong acceleration. So no normal creature would be able to survive something like that, at least for a while. And so apparently Taz is unrealistic, or the numbers that I made up are unrealistic. But yeah, this is how you can solve these types of problems for centripetal acceleration. So in the next part of this unit, we're going to start focusing on the agents that create centripetal forces. Because after all, if something goes in a circle, something must cause that. That something is an agent, and that's what we will examine starting in the next video. Thank you for watching, and I'll see you then.